Okay, so just in case there's some latecomers and whatever, I'll show you the movie now. This is a movie of conformal transformations by means of stereographic projection. So here it is. It even comes with music, just like a real movie.
Mobius transformations are among the most fundamental matters in geometry, with applications from brain mapping to relativity theory. A Mobius transformation sends each point on the plane to a corresponding point. They're built from four basic types. The simple translations. Dilations. Rotations. And inversions, which turn the plane inside out. Lines on the plane either remain lines or transform to circles, and right angles stay true. In general, a Mobius transformation can be a complicated combination of all four effects. The true unity of Mobius transformations is revealed by moving into the next dimension. Taking a cue from Bernard Riemann, we place a sphere above the plane. A light at the top shines through the spherical surface, illuminating the plane. As the sphere moves, the points on the plane follow. When the sphere translates, so does the plane. Raising the sphere gives dilation. Spin the sphere like a top, and the plane rotates. Rotation about a horizontal axis corresponds to inversion. Even the most complicated Mobius transformations are revealed to be simple motions of the sphere.
Okay, so I didn't make that. I had nothing to do with it. It's these people, but it has like several million hits on YouTube. This is the high definition version that you can obtain from the Minnesota website. Okay, right. So back to mathematics. So, as promised, I'm going to talk to you about conformally invariant differential operators, some sort of generalization of Maxwell's equations. We'll see how far we can take this and perhaps achieve a classification. Okay, so first I'll run through a few examples. I should say that all of this is sort of well-known material, especially to certain people in the audience who are responsible for developing it. Okay, so here are some examples. So, well, all right, we've seen the Maxwell equation in dimension 4 already. Also in dimension 2, although I sort of promised to stay clear of dimension 2, but it's true that in dimension 2, the Laplacian is invariant. One of the ways of saying this is to relate it to complex analysis. So there's a formula for it in terms of complex numbers. So differentiation with respect to complex variables. Also, one other thing that's clearly going to be invariant, and this is more of the flavor I want to talk about, is you've got some natural bundle, like the bundle of p-forms. So this is introducing my notation for the bundle of p-forms. And you've got exterior derivative going to p+1 forms. And of course, that doesn't depend on any coordinates or anything. It's completely coordinate-free definition on any smooth manifold whatsoever. So it certainly doesn't see the conformal structure. These three examples are a little bit too trivial regarding what's going on in more general. They're all really based on the fact that in even dimensions, the half-dimensional form split into two types. That's what I was saying before about the star operator being invariant in dimension 4 on two forms. So this process generalizes, and these are the two eigenspaces of the star operator in dimension 2m, and like the Laplacian in dimension 2, you can also think of it as d star d. So all of these are invariant for sort of fairly elementary reasons. But then there are some things which are invariant for maybe slightly deeper reasons. So I'll list a few of these now. There's the conformally killing equation. That was something that I talked about last time, how you would solve that in flat space. This equation, since it's very much geometrically connected with the idea of conformal geometry, this is going to be invariant in some suitable sense. I'm going to have to describe in a little while what invariance actually means more precisely, but let's just run through some of these examples before getting on to definitions. So there's that. There's the Dirac operator. That's one of the other most sort of fundamental differential operators on any Romanian manifold or spin manifold. That's going to be conformally invariant. There are these operators which were being discussed this morning by Judith and Junhua, and the Rita-Schringer operators, or Rita-Schringer operator. Okay, these things are conformally invariant too. So I'll tell you a little bit about these things as well. Then there's the so-called Yamabe operator. This comes in, there's two sort of standard names for this. There's either Yamabe operator or the Conformal Laplacian. So also known as the Conformal Laplacian. It's, many of these differential operators have some sort of well-known leading part and then some interesting additions that you have to put on in order to make them conformally invariant. So, I mean, I'm going to describe this as an example, and then there are sort of more exotic examples, such as in dimension, well, in arbitrary dimension, but most interesting in dimension 4, there's an operator which starts with the square of the Laplacian. So this is related to what Ian was talking about. Especially in dimension 4, this is a very interesting operator. And there's lots more besides. Okay, so there's plenty of examples. Okay, now we've got to discuss what it actually means to say something is conformally invariant. What is the meaning of this phrase? And this is actually a little bit subtle. And, well, there's a lot of different possible definitions. I can think of 8. Some of these things are different from each other as well. I mean, really, and some of them are equivalent in a non-trivial way. So you have to be very careful when someone says to you something's conformally invariant. You've got to really quiz them. Don't let them leave the room without telling you what they mean. And actually, of course, this might be a trick question because by and large they won't be able to tell you. But you have to think about this really carefully. Okay, now, what I'm going to do in this talk is talk about two meanings of conformal invariance. So, but there's one definition which well, this first definition I'm not even going to define, but I'm going to show you lots of examples of how it happens. This is invariance as an operator on a conformal manifold. So at least what I have in mind here is that there's some operator that you're going to write down in the first instance on a Romanian manifold, so like the Laplacian or something like that, and it's going to interact with conformal transformations in a very nice way, or interact with conformal scalings in a very, very nice way. So this is going to be some sort of something that you can check by computation at least, even if you don't know what the definition is. Okay, the second notion of invariance is, well, we saw the flat model of conformal geometry was the sphere under the action of this particular group, the Lorentz group in 2 dimensions higher up. And so you can ask for operators on the sphere which somehow respect this action. Actually, if you're going to talk about the Dirac operator, then you'd better increase your symmetry group a little bit as well. Instead of talking about SOM plus 1, 1, which is literally the group of conformal transformations of the sphere, you should pass to the double cover of that, which would be spin n plus 1, 1. But, I mean, these are all details. The point is that these two really quite different notions. One of them is invariance on a manifold, a general manifold somehow, and the other one is invariance on a space with a group acting on it. Right, so anyway, let's see how this happens. Okay, so I'm going to look at some examples now and check that the easy thing to check is actually this invariance as an operator on a conformal manifold, if this makes sense. So, yeah.
Can you just clarify what you mean by conformal manifold?
Right, so a conformal manifold is a manifold with, locally you have a Riemannian metric, a class of Riemannian metrics. Locally you have a class of Riemannian metrics. This class is defined by two Riemannian metrics are equivalent, are in the same conformal class if one is a scalar multiple of the other, just like this. This is a local equivalence relation amongst metrics. And I'm saying that this and this are conformally equivalent metrics. So a conformal manifold is a manifold where locally you have a metric but only defined up to this equivalence. I say locally because it depends what category you're in here, and normally one would be talking about smooth manifolds. But if you're talking about real analytic manifolds or more awkwardly conformal, complex manifolds, then you'd want this notion to be just a local notion. The quadric doesn't have a, yeah, that's why I keep on saying locally. Yeah, so in the smooth category you can just say globally because of partition of unity. Right, so, but all of these calculations are really just local calculations. So, and, you know, and I'm also trying to avoid admitting what this means. So you can think of this as actually being a metric with, you know, a genuine Riemannian metric with abstract indices on it somehow, whatever that means, or, and this is the more naive thing you can do, you can think of this as a matrix in local coordinates. Okay, so that's another reason why I'm always putting the word locally in front of everything. So you can think of this as explicitly just a positive definite matrix depending smoothly on on your coordinates. Okay, so in Romanian geometry you start with a metric, and the thing that you associate to that metric in order to do all of your calculus on your manifolds and so on is the Levi-Civita connection, the metric connection, the unique torsion-free connection which preserves the metric. And that's my notation for it. So for G, I'm going to associate nabla. Okay, so in the flat space, this will be coordinate derivative. Now, of course, if you change your metric, then the coordinate derivative, the Levi-Civita connection changes. And it changes in a way which, when you first look at it, is really a little bit complicated. And in particular, it involves derivatives of omega. So let me say what happens explicitly. This is how the connection changes when you look at it acting on vector fields. Right, so here is the Levi-Civita connection constructed from G. And here is the Levi-Civita connection constructed from G hat. Any time you have two connections, they're going to differ by some terms which don't involve any derivatives at all, some tensor. And the particular way in which the change of metric feeds into the variation is precisely like this, where this thing here, upsilon, is the derivative of omega. It's actually the logarithmic derivative of omega. It's the exterior derivative of omega divided by omega. Right, so given an omega, this thing here is a one form. And then this formula tells you how these things change. So let's just look at this, and even right away from this formula, I want to try and convince you that the conformal killing equation is conformally invariant. So I'm just going to write out this equation, but instead of having this index up here, b, I'm going to put it down. I'm going to lower it by means of the metric. So on a Riemannian manifold, so all of this is respect to a particular choice of Riemannian metric. I'm allowed to raise and lower indices. So let me just do that with the metric, with the metric G. Okay, so here it is. Right, so it's exactly the same expression, except I've written all the b's down here. Right, now, you look at this thing, and you notice that here, this part here, is skew in A and B. So if I were to take the symmetric part of both sides, these terms would disappear. Remember, my notation for taking the symmetric part of a tensor is to put parentheses around the indices. So that's what I'm going to do now. Right, so the same expression where I take the symmetric part, just take the average of this with the same thing with B and A interchanged, then these terms here drop out, and this one's already symmetric in A and B. So that one just stays there like that. Okay, now you look at this and you see that the way that this change is occurring is through terms which are pure trace. So if I were to further normalize both sides by removing the trace, so I've got a symmetric matrix, so I'm going to take out an appropriate multiple of, well, the identity in local coordinates to make it trace-free, then you would abolish this term. Okay, so the trace-free part, it's the same whether you compute it with respect to the rescaled metric g hat, or whether you construct it with respect to the original metric g. So in other words, this operator, which is the conformal killing operator, this is the first of these slightly non-trivial conformally invariant operators, satisfies this nice property. And you'd like to think of that as conformal invariance. Right? And this is a sort of operational way that you can check that things are conformally invariant. Right, now, this is again a simple example. And in order to really get the feel of this, if you're going to do this for yourselves, you've really got to go through a slightly more complicated example to make sure that you understand that there's lots of subtleties going on here. And apparently, when you first do this, you find amazing coincidences. So I'm going to do this for the Yamabe operator. Right? So the Yamabe operator has something to do with the Laplacian. The first thing is that on a conformal manifold, there's this equivalence class of metrics. Okay, so if you rescale the metric by a factor omega squared, as I've been doing, then you can talk about functions which rescale according to another power of omega. Let me say omega to the power w. So this thing here, this f, is not a function, but secretly it's a section of some appropriate line bundle defined by the conformal structure. But operationally, what it means is that if you have a metric in the conformal class, you have a genuine function. If you take a different metric in the conformal class, you are obliged to take your function and rescale it by an appropriate power of omega. Right? That's the operational definition of what it means to have a section of this line bundle. Okay, when you do that, then just the derivative, because this isn't a function, this is a density, the derivative, it's not just the exterior derivative anymore, it changes. So what I'm doing here is I'm really taking this formula for f hat, I'm differentiating it using the fact that I know that the derivative of omega is, well, the logarithmic derivative is this thing here, and then getting rid of the omegas again. So what it means is that on the bundle of conformal densities, that the connection changes. Now the other thing that we know is changing is that the way this derivative, the Levees connection here, how that changes on, for example, one forms. Let me combine these two. Right, so here I've got how it changes on a function with a particular weight, and here I've got how it changes. This is a more complicated formula, but it's a combination of the one we just had and the one on the previous slide. This is how the connection changes when you apply it to not just a regular one form here, but a one form with a weight. Right? So when you set all this up precisely, you have to talk about these things as being one forms tensored with a particular line bundle. Anyway, this is the formula. Now just bear with me while I do something slightly complicated. What I'm going to do is take these two formulas, right, this one, and I'm going to compose one with the other. All right, so, right, the first thing we get is, so what I'm going to do is look at how things change if I start with a function of a particular weight. Right, there it is. That was from the previous change. And I'm going to apply this derivative to it and use this formula to expand this. Right, so let's do that. Okay, so the first term you get is, so you get a bunch of terms. First term you get is this, except I've replaced omega by this expression. Right, then you get something with a w minus 1 in front of it. That's that. Then you get minus the same sort of thing with the indices around the other way. And then finally you get a term involving the metric, like that. Okay, so it's just combining these two derivatives. And now, remember that the Yamabe operator has something to do with the Laplacian. Let me now sum over A and B. In other words, take the trace with respect to A and B, and I'll get how the Laplacian changes. Right, so from this formula, you get this. Right, so this is, on the left-hand side, I'm just taking the trace of that. That gives me what I would define to be the Laplacian. The first term on the right-hand side, that's coming from here, gives me that. Then there are some terms which involve the derivative of f. Okay, they're occurring from here, here, and here. And also, there's a Leibniz rule when this one hits f. Okay, so there's these terms here involving derivatives of f. And then everything else is just actually linear in f, but involves epsilon and its derivatives. So you just do that. And now some magic happens. Right? So this is supposed to convince you that if you do one of these calculations and get it right, then something magic will happen. So on the next slide, I'm just going to take this formula and investigate consequences of it. Right? So if you want to do conformal differential geometry, you've got to do this calculation at least once in your life. All right? So here we go. So there's the next slide. That's exactly the same formula. Something special happens when W, the weight, is a particular value, namely 1 minus n over 2, because that means that these terms here will cancel out. So let's do that. Set W equal to minus 1 minus n over 2. Then the first term cancels out, and I've just rearranged the second these terms here, bearing in mind that I know now what W should be in order to get rid of this term. Right? And now okay, so things are getting more and more, well, they're simplifying a little bit, but still quite complicated. You compare this with how other things on the manifold are changing. The thing to look at now is the Ricci curvature, the scalar curvature. So the other thing you've got to work out is how the scalar curvature changes. And the scalar curvature changes like this. It changes by things which involve, well, derivatives of epsilon and epsilon itself. But the remarkable thing that happens is that this expression here is exactly the same as this expression here. Right? So by subtracting or adding an appropriate multiple of r to both sides here, you can get that this cancellation you can get everything to cancel. Right? So the punchline is that if I take exactly the right amount of scalar curvature here, you see that these numbers here, n minus 1 and a 4 and n minus 2 and so on, they're exactly what come out of this formula. If I take exactly this combination here, then everything cancels out. And the left-hand side and the right-hand side are equal. So this is with respect to any choice of metric in the conformal class. I don't know why this thing came up. Let me try and get rid of that. This is Microsoft oh, I just had to walk towards it in a threatening way. Yeah, you've got to treat computers rough, otherwise so this is invariant in this sense of sort of purely operational, calculational way. Now you can see that if you get into operators which are higher and higher order and stuff like that, this is going to get just totally out of hand. There's no way that you can proceed along these lines in a classification of invariant operators. So you've got to find a shortcut to all of this. I mean, this is something you've got to do for your soul, but you've got to somehow avoid this.
I can just clarify, when you took this trace,
yes.
you hooked with one metric on both sides.
No, on this side I'm hooking with the metric g, and on that side I'm hooking with the metric g hat. But yes. But what I've done is I've incorporated the weight into what g actually is. So when you think of g as being Yeah, yeah. The best way to think of G is it has values in one of these line bundles. It's a metric of a certain weight.
Naively, you think it would the same thing on both sides. There'd be
Yes.
a factor of omega.
There would, yes, but and you're right, and I've absorbed it. I've just absorbed it into my thought processes, whereby this weight here has changed from being a particular thing to being the same thing down by -2. That's right. Yeah. So it all makes sense if you say it right. Okay. And in particular, this operator, this what I'm calling the Conformal Laplacian, or the Yamabe. This is the Yamabe operator. It's actually an invariant operator between a couple of line bundles. So what I'm going to do now, I mean, and in fact, a good deal of this talk is actually just sort of, I don't know, talking about some notation, and in particular, talking about how you even bring representation theory into the game. So one of the notations I want to have is I want to have a notation for the bundle of densities of a particular weight. Okay, and that's my notation, putting the weight in square brackets like that. But the weight changes. This is an operator between different bundles. Right, so that's good for our soul and so on, but it's let's try and adopt a sort of higher point of view, or a different point of view, see if it sheds any light. Right, the different point of view is to look at SON11 invariance. This is on operations on the sphere, and you're trying to see whether they're invariant under this action of the group. Okay, so this is sort of Klein's view of geometry. Right, so recall, that the sphere is a homogeneous space. It's actually the quotient space of a nice group modulo a group which I've called P, a subgroup which I've called P. Okay, now, if you look at what P actually is, just at the Lie algebra, remember that the group of conformal transformations, that's SON plus 1, 1, if you look at its Lie algebra, it consists of rotations, dilations, inversions, and translations. Okay, if you want the stabilizer of a point, you should throw away the translations. Right, so this thing here, P, so this is the corresponding Lie algebra, but if you're not unhappy with that, just think of somehow P, the group, is being broken up into rotations, dilations, and inversions. There's part of it, the rotations and dilations, this is part of some general theory now, so I'm going to try and run some general theory past you. Whenever you have a parabolic subgroup, it breaks up into pieces, one of which is called the Levees of Algebra. This is, and in this particular case, you can identify the Levees of Algebra with a particular Lie algebra and exponentiate it and get back a particular Lie group. And what you get in this particular case is you get SON for the rotations and lambda greater than 0, say, for the dilations. So this is there's a subgroup of P which is just, I'm lying to you slightly, but it's essentially this direct product of SON with the positive real numbers. Okay, and then what you're going to look at on Sn, in order to set all this up, you've got to look at vector bundles which are invariant under the action of the group. Okay, the technical term for that is a homogeneous vector bundle, something which respects the action of the group. And if you want irreducible ones, which I do, so like line bundles and things like that, if you want irreducible ones, in general, a homogeneous vector bundle is determined by how P is acting on the vector space above the origin. It's determined by a representation of P. But to be irreducible, it's actually entirely carried by the representation on this subgroup. Okay, and so the irreducible ones are into one-to-one correspondence with the irreducible SON modules. That's just a fancy way of saying a vector space on which this group is acting irreducibly, together with how the scalars are acting. And in fact, what's really going on now, if you try and link this with the previous slide, this notion of conformal density, then the number W, and my conventions are such that there's actually a change of sign here, but the number W comes in how this part acts. Okay, so there's a bunch of homogeneous vector bundles on the sphere, and they're controlled by the way that these two pieces act. One of them is just controlled by a number, W, and the other one is controlled by the representation theory of SON. So the notation is I'm going to write V for an irreducible SON module and square brackets W to mean that this is how this is how the center is acting. Okay, so this is an irreducible Riemannian tensor bundle. It's just one of the usual, this corresponds on a Riemannian manifold to just one of the natural irreducible bundles that you would think of on a Riemannian manifold. And then this thing W here is an extra sort of weight that you put on it. Okay, that's the conformal weight. Okay, so we're getting into representation theory a little bit now. Right, so as in the title of the series of talk. By the way, the next talks don't depend on this talk. If you get lost with this talk, you can still come to the next talk. Right, so this is going to get a little bit heavy. I'm going to pack a few things in towards the end of this talk. Okay, so let's look at some examples of what I mean by Riemannian tensor bundle. So like the bundle of p-forms. The bundle of, this will be the symmetric, trace-free tensors with one index down of valence B. So that's my notation for the symmetric covariant B tensors which are trace-free. If you like Young tableau. I mean, one of the things is that you, Okay, one of the messages of this talk is that if you're going to do this sort of thing, you've got to be able to have some facility with representation theory. You have to sort of develop the usual sort of idiot savant capabilities. And one of these capabilities is be able to swap between various notations. So this is my notation for two forms. Okay, and if those in the audience who know what I'm talking about know what I'm talking about, and otherwise I'm not going to explain. This is the trace-free tensors with hook symmetry. This corresponds to tensors which have Riemann tensor symmetry, Weyl tensor symmetries, symmetries of the Riemann tensor which are in addition trace-free, and so on. Okay, so these things, or in certain dimensions, because you're in the orthogonal, in certain dimensions you might have to take, say, the self-dual part of one of these things. So like in 4 dimensions, the Weyl tensor breaks up into the self-dual part and anti-self-dual part, but only in 4 dimensions. Okay, so there's some notation for these things. This is not the best notation. None of these notations is the best notation. One of the things I want to try and point you to is what I think might be the best notation. Okay, but anyway, once you've got some of this notation, you can at least talk about differential operators on the 3-sphere. And in fact, here is a complete list of all of the invariant ones. Okay, a complete list of invariant operators under this group between irreducible tensor bundles. Okay, so they break into two families. There's a standard family and a non-standard family. The standard family, this is the first one. So what this is it's taking a tensor with so many symmetric indices on it, trace-free. It's applying so many derivatives, and it's taking the trace-free symmetric part. Okay, and with a suitable conformal weight, right, so this is generalization of the Killing equation, Killing operator, this is conformally invariant. Right, and then there's another one. And in fact, the composition of these two things is 0. This is a complex. Not only that, but it's actually locally exact. These are exactly the integrability conditions to be in the range of that. And then there's another one. And and let's see. And this generalizes the de Rham complex. If all of these parameters A and B are equal to 0, this is the de Rham complex. Okay, so there's a standard complex which is modeled on the de Rham complex. And then there's a few more called, imaginatively enough, non-standard ones. The non-standard ones, their weights are necessarily half integral, like 1 minus n over 2.
Implicitly in dimension 4, when you say A equals 0, the complex?
No, this is dimension 3. This is dimension 3.
Oh, dimension 3.
Yeah, this is dimension 3. Yeah. Oh, yeah. Oh, yes. Otherwise, you're going to object to the length. Let's just check the length is correct. This is 0 forms, 1 forms, 2 forms, 3 forms. Yeah. Right. Yeah. Right, so there's these things here. This non-standard family includes the Laplacian, or the Umabi operator.
But still, you don't need a twist because you're
You need a twist. I've said with suitable conformal weights. So in this,
okay, good.
right, in this one here, I've omitted all the conformal weights. Yeah, and here I've put them back in.
Yeah.
Yeah, basically I didn't have room, you know, because yeah, okay, right. Right, and I'm not going to say anything about the proof, but the proof is fairly, well, it involves Verma modules. If you know what Verma modules are, then this is what the proof involves. Okay, and now remarkably, I mean, this is the amazing thing, you can prove this without any of the explicit calculations I was doing before for the Umabi operator. All of these operators have conformally invariant, what I call curved analogues. That means you can add in curvature terms, just like for the Umabi operator, adding in an appropriate multiple of the scalar curvature. It makes it conformally invariant. The curvature terms that you have to add in for these other ones are just beyond belief. I mean, you would not want to even try and verify that one of these is conformally invariant, even if someone gave it to you. But it's true, nevertheless.
So that's sort of two assertions. So
Yep.
one is that if you have something on flat space, it has a cousin. Is it unique?
No.
So there's not
No.
just
Yep.
a fixed.
Yeah. You can. There may be some preference that you have, but yeah. But it's not necessarily unique. No.
But there is always existence.
Always existence. Yeah. Okay. Let me just give you a vague hint about the material that you have to use in order to prove that theorem. Okay. The good thing is that you can look at a particular differential operator, a particular conformal differential operator, and the way that one behaves controls everything else. This particular operator is called the conformal to Einstein operator. Okay, now this is a particular tensor which occurs naturally on a conformal manifold. It's defined in terms of any Romanian metric. So this is the Ricci curvature, this is the scalar curvature, and this is some appropriate linear combination of them. And this tensor here, this is actually not a p, but a rho. It's a Greek letter rho. This rho tensor here behaves in a very, very nice way under conformal transformations. Okay, so nice that the following operator actually turns out to be conformally invariant. So this is this is starting with a function, actually a function of conformal weight 1, and taking the trace-free part of, well, this will automatically be symmetric in A and B, and then adding on precisely this rho tensor. So this is a conformally invariant operator. It's on the list in the previous slide in dimension 3. This is true in general dimensions, and it's conformally invariant. Sigma should have weight 1. And it has a geometric interpretation. The geometric interpretation is in the title of the talk here. It's the operator on the previous slide in dimension 3 when A is 1 and B is 0. And its geometric meaning is that precisely when, at least when this thing is not equal to 0, in other words, generically, if you take your metric and multiply it by this, then you get an Einstein metric in the conformal class. So this differential operator is giving you the obstruction to finding, the kernel is giving you an obstruction to finding an Einstein metric in a given conformal class. Okay, now you cast your mind back to the first lecture. If you see an equation like this, you might try prolonging it and trying to solve it. So let's try doing that. Prolong this equation. So in other words, try and look at the solution set. Okay, now this is a second order equation. In order to prolong it, what you do is you introduce names for the first derivatives, call them mu. And then the differential equation itself says that if you take this thing here, then it should be pure trace, right? To say its trace-free part is 0. So you invent a name for the trace called rho. Right? And then it turns out that this system closes almost immediately. You can deduce from this what the derivative of rho is. And the derivative of rho, it's obliged to be related to mu. Okay, so you get a closed system right away. Now, one of the good ways of thinking of these closed systems, which I was talking about last time, is that this is actually a formula for a connection on a big bundle. Right? The big bundle consists of groups of tensors. It consists of a scalar called rho, a scalar called sigma, that's sigma, yes, a vector or one form called mu, and another scalar called rho. And you should think of this as actually a connection. This is a well-known connection in conformal geometry. This is called the Cartan connection. This is a viewpoint on the Cartan connection, but it's just created out of thin air by looking at this conformally invariant operator.
Is this a standard or non-standard?
This one here, this was a standard one. This is a standard one, yeah. It's one of the first non-trivial standard ones. Okay, and then what you do is you look at the Lie theoretic proof of the classification of all the invariant operators, and you use this as your principal ingredient in order to transfer what you know about the sphere into what you're trying to have constructed on a general conformal manifold. Okay, so it has a name, curve concentration principle. Okay, so much for that. Now, the rest of the talk, I want to just talk about a little bit about representation theory. And, you know, the message is that, this is something you've got to get your head around. If you avoid this, then, Right, let's look at, for example, SO9. Okay, what's the representation theory of SO9? Well, first of all, so I'm going to teach you a bit of hieroglyphics in case you don't know this already. So SO9 corresponds to this. This is a so-called Dynkin diagram. So all of the classical Lie groups are in association with so-called Dynkin diagrams. This is the Dynkin diagram for SO9. And the point is that not only can you denote the group itself by this Dynkin diagram, but you can also list its representations. And here they are. The representations are labeled by putting integers over the nodes of this Dynkin diagram. This is the so-called theorem of the highest weight. Okay, these are the irreducible representations of SO9. And A, B, and C here are arbitrary integers, and D is an even integer.
Why?
You'll see.
But, I mean,
Oh, you know
SO9,
why.
that's
Yeah,
SO9.
you know.
Sorry.
Yeah.
Sorry. Okay.
Yep. Okay. So, for example, this is R9 acted upon by SO9, right? So this is the defining representation. This is wedge 2 of the defining representation. This is wedge 3 of the defining representation. And wedge 4 is not putting 1 over the end, it's putting 2 over the end. So the last one here is a bit of a shock. Putting a 2 over the end there is wedge 4 of SO9. Of R9, sorry. This one here, for example, is the symmetric trace-free tensors of valence A. So it's, you can clearly see it's a very simple thing. This one here is recording the symmetries of the Weil tensor. So simultaneously, this notation is covering both the representations of SO9, and it's also, on the next slide, it's going to be describing the appropriate list of bundles that you have on your Romanian manifold. For spin 9, as JM was saying, As for spin 9, D here can be any integer, not an even integer. And in particular, if you put 1 over the end, that's the basic spin representation of spin 9. Spin 10, there's a similar sort of Dynkin diagram. It looks a little bit more fancy. Looks like that. That's the Dynkin diagram for SO10 or spin 10. And there are 2 basic spin representations for even-dimensional groups, and this is one of them. And there's a big difference between even dimensions and odd dimensions, both in conformal geometry and lots of other, life, the universe, and everything is different in even dimensions and odd dimensions, and it's reflected in the fact that Dynkin diagrams really look quite different. Okay, more representation theory. So on a Riemannian 9 manifold, what I was saying before is that you can just think of this as notation for the 1 forms. Okay, so precisely there's a representation of SO9 which this thing describes, and you're looking at the corresponding induced bundle. For me, they're induced from the coframe bundle. But then there are formulae for how these representations break up. So under SO9, if you have a couple of irreducible representations and tensor them together, you get something which is generally reducible, and it breaks up into pieces, and this is what happens in this particular example. These things then correspond exactly to various differential operators, these various pieces, because what you can do is you can take the Levees of Algebra connection to get you from here into this tensor product and then break it up into pieces. There's the trace part, the trace-free symmetric part, there's the skew part, and there's the divergence. And so that first one's like the conformal killing operator, this one's the exterior derivative, and this one's the divergence. Very familiar sorts of operators. But the point is that on a general Riemannian manifold, you can list lots and lots of invariant operators along this line, Riemannian invariant operators. So on a 9-dimensional spin manifold, for example, if you take the one forms, tensor with the basic spin representation, it breaks up into two irreducible parts. And each of these irreducible parts will correspond to a first-order operator, right? Because you're taking the one forms tensor this by means of the Levees of Algebra connection and then breaking it all up into pieces. This first one, yep.
I asked this before, but how, so you're thinking of these things as the image, I guess you're working locally or something.
Oh, no, yeah.
But when you go to 3 forms, you're going to still think of it as coming from 1 forms? You're going to,
3 forms? So this is I'm taking a first-order differential operator, and that's reflected in the fact that I've got 1 forms here. That's a 1 here, not A. And now I'm breaking the image up into its irreducible parts. I'm doing the sort of... this is not...
Those ones mean 2 different things. The one on the left is your differential operator,
Yes.
and the one on the right is your vector.
Yes, it is. Yes, I should have...
Now
Yeah. Okay, this isn't a very good slide. Yeah, sorry. And right, this...
The second part is much better than the first.
Yeah, that's right.
So his notation for nabla is that, because that's the module it corresponds to, and then it acts on some bundle, and it'll tensor.
And then you break it up. Okay, so this is to be read 1 forms tensor V. This is the symbol of the. What I'm doing is classifying the symbol of the operator. Yeah. Okay, so if you take the operator itself to be the Levees of Algebra connection, this first one has a name, it's called the twistor operator. The second one has a name, it's called the Dirac operator. So on a Riemannian manifold, you can start writing down differential operators using this notation, and you'd be a fool not to, really, I mean, because otherwise it just gets totally out of control. All right, so now what about invariant operators? All right, so remember, so that I'm going to now try and sort of list some conformally invariant operators, at least the bundles they go between. I've pretty much run out of time, so nearly there. So what you do is you this has got something to do with the representation theory of the big group, right? That's 1 dimension up, right? So SO10-1. So you've got an extra vertex on your Dynkin diagram. And the killing operator and all these various other things then find interpretation in terms of not just operators between these various Riemannian bundles, but somehow this extra node here is carrying the conformal weight in a way which I'm not going to go into, apart from the fact that the Yamabe operator, this is the right number. Right? It's -1 minus n over 2 going to -1 minus n over 2. So various different operators which are invariant for various different weights. And in fact, all of these operators in all dimensions are invariant, both in this really strong sense of there's a version on a conformal manifold and also on the sphere. Okay, so let's just look at some... if you write out that complex which I had before, which was the analog of the Dirac complex in this notation, you get that. Actually, the 3-sphere is also a homogeneous space for many other simple Lie groups, not just the conformal Lie group, but well, at least 3 others. So there's it's a homogeneous space under SP4 as well. So this is a corresponding thing you get there, and it's a homogeneous space under SU21. So there's these various complexes. which arise just on the 3-sphere, but I think of it as a symmetric under different groups. Okay, but punchline is you should beware the 4-sphere, because on the 4-sphere, the pattern looks like, this is the pattern for standard operators. This is what the Dirac complex looks like, where I've broken up the two forms into the self-dual and anti-self-dual parts. So this, and then of course there's this operator here, which is just a composition of going around from there to there. This is a list of invariant operators. But then really surprisingly, there's this operator which goes from here to here, which doesn't commute with this pattern at all. Right? But this thing here, in the Dirac case, this would be the square of the Laplacian plus lower order terms. And that red one there is non-standard. Most of these, in even dimensions, things go wrong. Big difference between even and odd. In even dimensions, most of these operators have conformally invariant curved analogues, but some do not. So let me just tell you about this. The standard ones all do. Right? So the ones that are in white here all do. The non-standard ones, the status is still unknown in general. It's some sort of unhappy symbol there. So various things like the Laplacian, which is a degenerate case of one of these red arrows. That one's okay. That's known to Bateman or Yamabe or actually Dirac. Various people have noticed that. The square of the Laplacian is okay. And even in higher dimensions, there are some analogues of these operators, very subtle operators, due to Graham, Jenny, Mason, and Sparling, known as GJMS operators. But the square in dimension 4, the square of the Laplacian is conformally invariant, but only just. I mean, you can just add in curvature correction terms and make it invariant. But the cube of the Laplacian is not. So Robin Graham checked by hand that you cannot put any possible correction terms in. And more generally than that, Gova and Hirachi have a more general argument, more abstract argument for why you cannot put in more correction terms. Okay, and in general it's not known. These are just on scalars. What happens when you put in tensors? I don't know. There's some sort of conjecture in. There's another version of invariance due to myself and Jan, which where none of these outside ones have curved invariant analogues. Okay, so here's some references, and I've run out of time, so I'll stop now. Thank you.
I'm having a hard time when someone tells me here's an invariant operator, guessing what the weight should be that you go with it. Is there a way
Yes.
Other than
yes.
Do I need to know that Bacon diagram technology to guess the weight, or do you have some other?
Yeah, I can tell you what the mnemonics are. So yeah, that's right. So for example, why is it that these various? I mean, there's a slightly non-trivial relationship between what the weight is and what these numbers actually are. This A here and here and here. Okay, so there's some linear relationship between them, right? But in order for these things even to have a hope of having an invariant operator between them, right? Then there must be well, there are two ways of saying it. First of all, the best way of saying it is that the corresponding weights must be equivalent must be in the same orbit of the affine action of the Weil group. So you have to add rho. So this thing here, if you add rho to this, get A plus 1, B plus 1, and add rho to that. In fact, you can even see that this one's just actually a reflection of that one. So these weights here are obtained by the action of the Weil group on the rho translated weight, the affine action of the Weil group. So they must be related by the affine action of the Weil group. Okay, that's the sort of best answer. And if you just wanted to know something a little bit less refined than that, you could just say that, well, in order for that to happen, they have to be the same distance from the origin. Right? So they have to have, and that's actually controlled by the quadratic Casimir operator, how far the weight is from the origin. So there's a quadratic equation that you can write down, which which gives you one single constraint amongst these weights in order to have an operator between them. Yeah, so it's yes, but it involves the full sort of mnemonics of these diagrams. Yeah.
One more question. Thank you.
Thank you.